The morning of March 19, 1945, found Lieutenant Commander Joseph O'Callaghan gripping the steel railing of USS Franklin as the ship shuddered violently beneath him. Another explosion tore through the vessel, the 23rd, in less than an hour. Black smoke poured from every hatch and doorway, choking and thick, as sailors desperately aimed fog nozzles into the raging inferno consuming the hangar deck. The heat was unbearable, the noise deafening, the scene almost beyond comprehension. 3 years earlier, most naval officers would have dismissed the idea as ridiculous, using what looked like garden sprayers to battle a fuel fire aboard an aircraft carrier. The notion would have drawn laughter from ready rooms and officers' clubs across the fleet. Yet on this terrifying morning, those same fog nozzles represented the only barrier between 700 men and certain death. The remarkable journey that brought these humble devices from a New York firefighter's inspired idea to standard equipment on every American warship is one of the most extraordinary transformations in military history. It started not in the plush offices of admirals or with university-trained engineers, but with men who knew fire intimately. Men who battled blazes in crowded tenement buildings and massive warehouse complexes understood something fundamental that naval tradition had overlooked. Sometimes the finest mist of water could accomplish what torrential streams could not. None of them realized then that their stubborn refusal to accept institutional rejection would completely reshape how naval warfare was fought, ultimately saving not just hundreds of ships, but tens of thousands of lives, and establishing firefighting practices that would remain standard for more than 50 years. To grasp how this transformation unfolded, we must journey back to the catastrophic event that set everything in motion. A Sunday morning 4 years earlier that would force the Navy to confront everything it believed about fighting fires at sea. That crisis began on December 7, 1941, when Japanese aircraft descended on Pearl Harbor. The Sunday morning attack ignited fires that exposed a devastating truth about American naval preparedness. The scale of destruction was staggering and immediate. Within less than 2 hours, the Pacific Fleet suffered losses so catastrophic they would reshape American naval thinking for generations to come. The Arizona exploded with terrifying violence and sank in just 9 minutes. Her forward magazine detonated with such devastating force that the blast wave shattered windows across miles of ocean and was felt throughout Oahu. The explosion lifted the 33,000-ton battleship partially out of the water before she settled back and began her final descent into the harbor. Over 1,100 men died, most of them below decks, where fire and flooding overwhelmed the damage control personnel who lacked the proper tools and training to save their ship. The forward magazine blast was so powerful it broke the vessel's back, sending the bow section plunging to the harbor bottom while fires consumed everything aft of the break. The Oklahoma capsized in 12 minutes, rolling slowly toward port as torpedo after torpedo struck her hull. 429 men became trapped inside as the battleship turned turtle, her bottom exposed to the sky, while hundreds of sailors inside pounded desperately on the steel hull. Rescue teams could hear them for days, cutting through metal with cutting torches in a frantic race against time, asphyxiation and rising water inside the inverted compartments. Some men were pulled to safety, but most perished in the darkness. The West Virginia settled into the harbor mud, her decks ablaze with burning oil spilled from ruptured fuel tanks. The fires burned for roughly 30 hours, fed by oil floating across the water's surface and petroleum vapors rising from damaged tanks scattered throughout the ship. Firefighting crews fought desperately to contain the flames, but they lacked the equipment and techniques necessary to extinguish fires burning on water or to cool superheated spaces filled with petroleum vapor. Over 3 days, the ship slowly settled as flooding spread through compartments damaged by torpedoes and bombs, eventually coming to rest on the bottom with only her superstructure visible above the surface. 166 men perished aboard the California as she burned while slowly sinking over 3 days. Fires raging through her superstructure as water rose through her lower compartments. 2 torpedoes and a bomb had opened her hull to the sea, but it was fire as much as flooding that sealed her fate. 104 men were killed and 61 wounded as firefighting teams struggled unsuccessfully against both elements. The ship eventually settled to the bottom with her decks awash, yet another victim of inadequate firefighting capability. The Nevada became the only battleship to get underway during the attack, her crew desperate to escape the inferno of battleship row. But fires from bomb hits and strafing runs spread faster than her damage control parties could manage. With flames threatening to reach her magazines and trigger another catastrophic explosion like the Arizona, her captain made the agonizing decision to beach the ship rather than risk blocking the harbor channel. Nevada ran aground off Hospital Point, still burning, her escape attempt thwarted by fires that could not be contained. The pattern was unmistakable and deeply damning. In a single morning, the United States Navy lost more ships to fire and its effects than to direct enemy action. Bombs and torpedoes started the fires, but it was the Navy's inability to control those fires that transformed damage that should have been survivable into total loss. Ships that deserved to be saved were consumed by flames that spread unchecked through steel corridors, ignited ammunition magazines, and overwhelmed damage control parties armed with inadequate tools and outdated techniques. Among those who studied the catastrophe with particular focus was Lieutenant Harold J. Burke, a Navy reservist who had spent 20 years with the New York City Fire Department before being called to active duty. His path to this moment had been shaped by decades of hard-won experience, fighting fires in one of America's most demanding urban environments. Harold J. Burke had joined the FDNY in the early 1920s, entering a fire service still dominated by horse-drawn equipment and techniques that had changed little since the previous century. New York in those years was a city of stark contrasts, gleaming skyscrapers rising across Manhattan, while immigrant tenements crowded the Lower East Side. Modern department stores displayed the latest goods, while warehouses stuffed with combustible materials lined the waterfront. Working his way up through the ranks during a period of rapid transformation in American firefighting, Burke fought blazes in 5-story walk-up tenements where families lived packed 20 to a floor, buildings with wooden interiors that burned like kindling once fire took hold. He battled warehouse fires where burning turpentine, paint, and industrial chemicals created conditions that conventional firefighting methods barely touched. Through these experiences, he learned that different fires require different solutions, that what worked on burning wood might spread flames through burning liquids, that sometimes less water applied correctly accomplished more than torrents supplied incorrectly. By the time war clouds gathered in the late 1930s, Burke had risen to deputy chief of the FDNY, one of the most demanding firefighting positions in America. As deputy chief, he oversaw operations across multiple boroughs, coordinating responses to major fires and developing standardized procedures that could be applied consistently across the department. He was responsible for training, equipment acquisition, and tactical doctrine, experience that would later prove invaluable when applied to naval firefighting. The FDNY of Burke's era stood at the forefront of firefighting innovation. Municipal fire departments fought fires daily, learning through painful experience what worked and what failed. They experimented with new equipment, refined techniques, and shared knowledge across departments. By 1940, progressive fire departments had largely adopted fog nozzles for specific applications, particularly fires involving flammable liquids where solid streams proved not just ineffective, but actively dangerous. Burke had witnessed firsthand how fog nozzles transformed outcomes in industrial fires. He had seen warehouse fires that solid streams only spread, brought under control within minutes once fog patterns were applied. He had watched petroleum fires that conventional tactics could not touch get extinguished by the steam-generating capability of properly applied water fog. His understanding of physics, heat absorption, and steam generation, the tactical applications of water curtains and indirect application, the importance of cooling superheated gases before attempting interior attacks, set him apart from officers whose knowledge came purely from naval tradition. When Burke received his commission as a Navy lieutenant and reported for active duty, he brought with him this wealth of practical knowledge. His initial assignment was to inspect damage control procedures aboard ships in port, evaluating their readiness for combat operations. What he found deeply alarmed him. Naval firefighting in 1941 remained rooted in traditions established during the Age of Sail. The basic approach had changed remarkably little over centuries. When fire broke out, sailors formed bucket brigades to pass water hand to hand from the nearest source. When pumps were available, they directed solid streams of water at the base of flames through straight-bore nozzles that had barely evolved since the 1800s. The emphasis was on volume, pouring off water on any fire, and eventually it must go out. This doctrine worked adequately for the fires most likely to occur on wooden ships, burning canvas, smoldering rope, fires in crew quarters or storage spaces. The fires were relatively small, contained within compartments that could be sealed off, and generally involved ordinary combustibles that responded to cooling from water application. Naval tradition emphasized aggressive interior attacks, getting as close to the fire as possible with the largest hose capable of fitting through passageways and overwhelming flames with sheer volume of water. But modern warships bore little resemblance to their wooden ancestors. Steel construction meant fires behaved differently, with metal conducting heat throughout structures and creating superheated spaces that were death traps for firefighters. The introduction of aviation operations on carriers brought massive quantities of aviation gasoline aboard, stored in tanks, distributed throughout the ship, and pumped through miles of piping to fueling stations on hangar and flight decks. A single carrier might carry over 150,000 gallons of aviation gasoline, along with bombs, rockets, and ammunition for dozens of aircraft. The vulnerability this created was staggering, yet the Navy's firefighting doctrine had not evolved to match the threat. Inspecting ships equipped with fire mains and hydrants positioned throughout, Burke found straight-bore nozzles of various sizes, from small handheld types to massive monitors capable of delivering thousands of gallons per minute. He observed damage control parties trained to stretch hoses, connect to hydrants, and direct solid streams at fires. What he did not find was any recognition that solid streams were fundamentally inadequate for the types of fires modern naval warfare would create. When he questioned damage control officers about procedures for fighting aviation gasoline fires, he received answers that revealed dangerous ignorance. They would direct solid streams at the base of flames, they explained, overwhelming the fire with volume. When Burke pointed out that solid streams scatter burning gasoline and spread fire rather than extinguishing it, he was met with blank stares or irritation at civilian interference with naval traditions. The Navy's damage control schools taught bucket brigade procedures unchanged since wooden ships. They emphasized the importance of maintaining pressure in fire mains, of organizing men efficiently to stretch hoses, of directing streams at the seat of fire. They taught almost nothing about the behavior of different types of fires, about the physics of heat transfer and steam generation, about the dangers of applying water to burning liquids, about the importance of cooling superheated spaces before entry. Burke submitted report after report documenting these deficiencies, recommending adoption of fog nozzles and modernized training. His reports were filed away, acknowledged with perfunctory responses, but producing no actual changes. The Navy had been fighting fires the same way for generations. Why should they change now based on the recommendations of a civilian firefighter who had never served at sea? Then came Pearl Harbor, and everything changed. In the days and weeks following December 7th, damage assessment teams fanned across Pearl Harbor to document what had happened and why. They photographed destroyed ships from every angle, interviewed survivors, examined burned compartments, and attempted to reconstruct the sequence of events that had turned survivable damage into catastrophic loss. Obtaining copies of these reports and photographs through his position in the Navy's Damage Control Assessment Office, Burke saw confirmation of his worst fears. Ship after ship showed the same pattern. Initial damage from bombs or torpedoes was followed by fires that spread out of control, overwhelming damage control parties and ultimately dooming vessels that should have survived. The photographs told stories of desperate improvisation and tragic failure. Firefighting teams had attacked fires with solid streams, only to watch flames spread as water scattered burning oil across decks and into adjacent compartments. They had directed powerful streams into burning spaces, only to create so much flooding that ships capsized or sank before fires could be controlled. They had been driven back again and again by heat and smoke they had no way to cool or dissipate, forced to watch helplessly as flames consumed their ships. Survivor accounts provided even more damning evidence. Sailors described attacking fires with the largest hoses they could deploy, pouring thousands of gallons into burning spaces, only to watch flames intensify as water pressure scattered burning petroleum. They described being unable to approach within 50 feet of fires because radiant heat was too intense, unable to cool spaces enough to make entry. They described ammunition cooking off because they had no way to cool magazines threatened by adjacent fires, explosions that killed firefighting personnel and spread fire to new areas. Most tellingly, they described the psychological impact of facing fires they had no effective means to fight. Training had taught them that solid streams were the answer to any fire. When those streams failed, when fires grew despite their efforts, sailors experienced a profound sense of helplessness. Some abandoned firefighting efforts prematurely, convinced nothing could stop the flames. Others persisted beyond the point of safety, dying in futile attempts to control fires without adequate tools. Compiling this evidence into a comprehensive report, arguing for immediate adoption of fog nozzles and complete overhaul of naval firefighting training, Burke documented municipal firefighting experience with similar fires, provided data on fog nozzle effectiveness against burning petroleum, explained the physics of why fog patterns succeeded where solid streams failed, and outlined a training program that could transform naval damage control capabilities within months. His report landed on desks throughout the Bureau of Ships and the Navy's Training Command. Once again, it was met with skepticism bordering on hostility. Officers questioned whether municipal firefighting experience was relevant to shipboard conditions. They argued that fog nozzles looked inadequate, that the fine mist appeared to be less water and therefore less effective. They suggested that better training in traditional methods was all that was needed, not wholesale equipment changes. The institutional resistance Burke faced was rooted in multiple factors. Adopting his recommendations would require admitting that Pearl Harbor losses were partly due to inadequate doctrine, not just surprise attack. It would mean replacing equipment fleet-wide at significant cost. It would require rewriting training manuals and retraining thousands of sailors. Most fundamentally, it would challenge naval traditions that stretched back centuries, traditions that defined institutional identity and professional pride. Finding himself fighting not just technical ignorance, but cultural inertia, bureaucratic self-protection, and the natural human resistance to admitting error, Burke's recommendations were revolutionary, and revolutions are never welcomed by established institutions, even when evidence demands change. While Burke fought his bureaucratic battles, the war continued and ships continued to burn. Each new loss provided fresh evidence that traditional firefighting methods were inadequate, but also created pressure to focus on building new ships, rather than changing how fires were fought on existing ones. On May 8, 1942, carrier Lexington succumbed to uncontrolled fires following damage at the Battle of Coral Sea. The carrier had survived multiple torpedo and bomb hits during the battle, damage that was serious but should have been survivable. Her damage control parties fought the initial fires successfully, and for several hours it appeared the ship might be saved. Then fuel vapors that had accumulated in compartments damaged by torpedoes found an ignition source, triggering a massive explosion that started fires deep in the ship's interior. Firefighting teams attacked these new fires with solid streams, but the flames were fed by leaking aviation gasoline and hydraulic fluid that solid streams could not effectively extinguish. Heat built up in compartments adjacent to the fires, cooking off ammunition and starting secondary fires faster than crews could contain them. Within hours, fires were burning out of control through multiple decks. Explosions rocked the ship as magazines detonated. 216 men died before Lexington had to be abandoned and scuttled. A capital ship, one of only 4 fleet carriers available to the Pacific Fleet, was lost not to enemy action alone, but to the Navy's inability to control the fires that followed initial damage. On September 15, 1942, Carrier Wasp was torpedoed by Japanese submarine I-19, southeast of San Cristobal Island in the Solomons. 3 torpedoes struck the carrier's starboard side, rupturing aviation gasoline tanks and starting massive fires on the hangar deck. Aviation gasoline poured from ruptured tanks, creating pools of burning fuel that spread across the hangar deck and into adjacent spaces. DC parties directed solid streams at these fires, but the high-pressure water scattered burning gasoline, spreading flames rather than extinguishing them. Within 30 minutes, fires were burning on 3 decks. Ammunition began cooking off, killing damage control personnel and preventing close approach to the fires. The ship lost electrical power, meaning pumps could not maintain adequate pressure in fire mains. Firefighting teams continued fighting with reduced water pressure, but solid streams that were barely effective at full pressure accomplished nothing at half pressure. Heat built to levels that began warping steel structures. After 3 hours of futile firefighting efforts, the order was given to abandon ship. 193 men were killed. Wasp was scuttled by destroyer torpedoes, another carrier lost to fires that should have been controllable. The pattern repeated with smaller vessels. Destroyers hit by bombs or torpedoes found their damage control parties overwhelmed by fires that spread faster than they could be contained. The close quarters on destroyers meant fires could reach magazines within minutes, creating catastrophic explosions. Cruisers survived torpedo hits only to be consumed by fires that traditional methods could not control. Each loss provided more evidence that Burke's warnings were correct, but institutional inertia continued to prevent change. By late 1942, the mounting toll of ships lost to fire was becoming impossible to ignore. Admiral Ernest King, Commander-in-Chief of the U.S. fleet, demanded answers about why so many damaged ships were being lost to fire rather than saved by damage control. His inquiries put pressure on the Bureau of Ships to produce results and explain why the Navy seemed unable to control fires that municipal fire departments routinely handled. This created an opening for Burke, but he needed an ally with sufficient authority to force change through bureaucratic resistance. That ally came in the form of Rear Admiral Edward L. Cochrane, who took over as Chief of the Bureau of Ships on November 1, 1942. Cochrane was an engineer by training, a 1911 Naval Academy graduate who had specialized in ship construction and propulsion systems throughout his career. Unlike many flag officers whose experience was primarily operational, Cochrane understood technical systems at a deep level. He had overseen destroyer construction during World War I, served as supervisor of shipbuilding at multiple yards, and earned a reputation for innovation and willingness to challenge conventional wisdom when engineering principles demanded it. Cochrane's appointment came at a critical moment. The Navy was in the midst of the largest shipbuilding program in history, with hundreds of new vessels under construction. But ships being lost to fire at sea threatened to undermine this massive investment. Cochrane immediately demanded a comprehensive review of damage control capabilities, particularly firefighting equipment and training. Seeing his opportunity, Burke arranged a meeting with Cochrane through intermediaries to present his case for fog nozzles. The meeting did not go as Burke initially expected. Cochrane listened to Burke's arguments about fog nozzles' superiority, then peppered him with technical questions that revealed a sophisticated understanding of thermodynamics, fluid mechanics, and heat transfer. Burke fielded each technical question methodically, walking through not just the theory, but drawing on his real experience with the New York Fire Department. He detailed specific incidents where fog nozzles had outperformed traditional solid streams, broke down the tactical advantages in various scenarios, and was honest about situations where solid streams still held the upper hand. Cochrane watched carefully, impressed by both Burke's grasp of the technical fundamentals and his practical battlefield wisdom, yet doubt lingered in his mind. The fog nozzles looked so delicate, so insubstantial. The mist they produced seemed inadequate compared to the forceful solid stream. How could something that appeared to spray less water actually prove more effective? Burke walked him through the physics, explaining surface area and heat transfer efficiency, but explanations alone would not sway him. Cochrane needed tangible proof. The Navy doesn't revolutionize its equipment and procedures based on theories and city fire department experience, he told Burke directly. Before I can recommend this to the leadership, you'll have to show me that fog nozzles genuinely perform better than solid streams in controlled test conditions where we can actually measure the results. Burke accepted immediately. Give me a week, Admiral. I'll set up a demonstration that will show you exactly what these nozzles can do. That week became a blur of preparation for what might be the most critical test of Burke's career. He secured access to a controlled burn facility at a naval yard, a place where he could safely conduct realistic fire experiments. He obtained 100-octane aviation gasoline, the same fuel that ran carrier aircraft and created the deadliest shipboard fires. He constructed a mock compartment with steel walls, ceilings, and decks, salvaged from decommissioned vessels, replicating the tight, restrictive spaces found aboard naval ships with minimal air circulation. He gathered solid-bore nozzles of various sizes alongside several Rockwood fog nozzles. He brought in experienced firefighters from both the New York Fire Department and Navy damage control training programs to operate the equipment, guaranteeing that any variations in performance would stem from the equipment itself, not the skill of the operator. Most significantly, he installed an array of measurement devices to capture objective data. Thermocouples positioned throughout the compartment would track temperature readings before water application, during application, and after. Flow measurement devices would show exactly how many gallons were deployed. Stopwatches would record the minutes and seconds needed for fire suppression and total extinguishment. Burke was determined to collect evidence that could not be dismissed as mere opinion or subjective interpretation. When Cochrane arrived for the test, he brought several high-ranking officials from the Bureau of Ships and Navy Training Headquarters. Some genuinely wanted to see whether Burke's theory held up under rigorous testing. Others came expecting to watch civilian interference in Navy traditions fail, ready to dismiss fog nozzles as impractical. Burke began with a briefing on what they would observe. We're going to conduct 3 separate burn tests in this compartment. The first will use a 2.5-inch solid stream, standard Navy damage control equipment operated by seasoned professionals. The second will use a fog nozzle on identical hose, also operated by highly trained personnel. The third will pit both methods head-to-head simultaneously. Each test will ignite 20 gallons of aviation gasoline, enough to generate a severe fire, yet controlled enough to be handled safely. The first test commenced. Aviation gasoline pooled across the steel deck and ignited instantly, transforming the compartment into a raging inferno, with flames shooting upward and thick black smoke billowing into the air. The radiant heat was enormous. Observers standing 30 feet from the entrance could feel the warmth radiating against their skin. A damage control team in protective gear moved forward with the solid stream, applying high-pressure water directly to the fire's base. The result unfolded exactly as Burke anticipated. The forceful stream struck the burning gasoline and splattered it, pushing flames outward across a wider space. Much of the water passed straight through the flames without absorbing sufficient heat, simply flowing away as wasted water. Flames reduced slightly where the stream made direct contact, but surged higher across areas where scattered fuel ignited fresh portions of the deck. After 2 solid minutes of steady application, fire still raged across most of the compartment. 5 minutes elapsed before the fire finally extinguished, yet the compartment now held several inches of standing water. The air remained dangerously hot, and this approach had clearly struggled with even a relatively modest fire. "Take note of the time," Burke told the gathering. 5 minutes and 7 seconds. Look at the water consumption, 420 gallons. The compartment remains too dangerous to enter, over 400 degrees. And observe the flooding, which on an actual damaged vessel could compromise stability and seaworthiness. The second test began after the compartment dried and reset. This time, Burke's team approached with the fog nozzle set to its wide spray pattern. Rather than directing the fog straight at the flames, they aimed it above them, producing a mist of droplets that descended through the burning area while simultaneously cooling the superheated atmosphere and smoke in the upper reaches. The change was instantaneous and striking. Within 30 seconds, flames visibly shrank throughout the space. 60 seconds in, only small flames remained. 90 seconds later, no flames remained anywhere. Burke's crew swept the fog pattern across the walls and ceiling, cooling the entire compartment thoroughly. When they stepped out, the instruments showed the compartment temperature had plummeted from over 1,200 degrees down to less than 300 degrees. "Time to full extinguishment," Burke reported. 1 minute, 32 seconds. Water used, just 75 gallons. Compartment is now cool enough for safe entry. Almost no water accumulation. This demonstrates the advantage, gentlemen. The fog pattern creates vastly greater surface area for absorbing heat, converts water to steam far more efficiently, and achieves superior results with significantly less water. The third test combined both methods in the same burning compartment. Two crews entered simultaneously, one deploying solid stream, the other with fog nozzle. The fog team suppressed the fire in under 60 seconds. The solid stream crew continued battling scattered flame pockets 3 minutes later when the exercise was stopped. Cochrane absorbed what he had witnessed. The numbers made the case conclusively. Fog nozzles controlled fires faster, using dramatically less water, and left spaces safer and cooler. The visual proof was equally powerful. What had appeared insubstantial mist had proven dramatically superior to the formidable-looking solid streams. Lieutenant Burke, Cochrane addressed him, "I'm satisfied. The challenge now becomes how quickly we can outfit the entire fleet and instruct our personnel in the new methods." Some officers tried interjecting counter-arguments. Fog nozzles might function in test settings, but would struggle in wartime confusion. Sailors would lack the training to use them properly. The expenses of re-equipping hundreds of ships seemed prohibitive. Cochrane stopped them abruptly. "I watched fog nozzles control fires 3 times faster while using just 1/5 the water volume. Every day we postpone implementing this technology, we expose additional ships and sailors to preventable fire losses. This begins immediately. Lieutenant Burke, you have responsibility for establishing a comprehensive training initiative for the entire fleet. You will receive whatever resources are necessary." Burke suddenly confronted an enormous responsibility. A training program that would reach thousands of sailors across numerous naval bases, construct dozens of new training facilities, and prepare hundreds of instructors. Military organizations typically needed years for transformations of such scope. Burke possessed months, at most, before the fleet would encounter actual combat situations where these capabilities would be essential. Burke's first move involved assembling a team. Through Navy personnel databases, Burke located Lieutenant Kildaff, a reserve officer who had worked as a firefighter with the Boston Fire Department before military service. Kildaff possessed experience both as a firefighter and as a training professional, having previously managed the Boston Fire Department's recruit training program. Burke and Kildaff joined forces to form the leadership group that would fundamentally transform naval damage control instruction. Their methodology represented innovation for military training standards of that period. Rather than classroom learning, followed by limited hands-on practice, Burke and Kildaff created a program centered on realistic burn training that exposed sailors to conditions matching actual shipboard fires as closely as safety permitted. They understood that competence emerged from experience, that sailors who had successfully fought authentic training fires would function effectively in genuine combat circumstances. The initial school opened at Boston Naval Yard in June 1942, specifically at the Navy's installation on K Street in South Boston. Burke and Kildaff spent considerable time creating and constructing the training equipment. They fabricated full-scale compartment replicas using steel walls, ceilings, and decks removed from vessels being scrapped. These mock compartments matched the constrained dimensions, narrow entry points, and insufficient ventilation typical of naval vessels. They incorporated realistic fire scenarios utilizing controlled fuel burns, capable of producing severe heat and smoke while maintaining acceptable safety margins for trainees. The main feature was a flight deck reproduction capable of simulating the devastating aviation fuel fires that had destroyed the Lexington and Wasp. The structure stretched 50 feet in length and 30 feet in width, built with steel decking, overhead ventilation systems that could be sealed to simulate battle damage, and fuel systems that could distribute pools of burning gasoline across the surface. Integrated safety features included automatic shutoffs, installed extinguishing systems, and emergency exits, yet students experienced authentic flames, scorching temperatures, and thick smoke. Additional training setups included an engine compartment replica showing fuel oil fires, a bunk compartment displaying typical fire scenarios, plus numerous compact spaces for instructing fundamental suppression techniques. Every installation included monitoring equipment, allowing instructors to supervise conditions and maintain student safety while stretching their capabilities. Burke and Kildaff structured the training curriculum in a progressive sequence from foundational to advanced. The opening day included classroom sessions on combustion behavior, thermal transfer principles, and the science underpinning fog technology. Students absorbed information on why fog techniques succeeded, how to regulate nozzles for varying situations, and circumstances when solid streams remained preferable. Classroom instruction, however, comprised merely 4 hours. Practical exercise consumed the remainder. Trainees dressed in protective equipment, helmets, gloves, thick protective clothing. They practiced fitting and checking emergency air apparatus and working in coordinated groups. Following this preparation, they entered the training compartment for their opening live fire experience. Instructors ignited a controlled burn and students rehearsed moving toward the fire, deploying fog patterns from secure distances, proceeding forward as fire intensity decreased, and achieving complete extinguishment. The progression was repeated continuously until reactions became instinctive. Day 2 introduced greater challenge. Students battled more substantial fires in increasingly lifelike conditions. They mastered forcing entry through doors sealed shut by heat and pressure buildup. They maneuvered hose lines through smoke-filled passages. They experienced flashover situations in which superheated compartment air spontaneously combusts, inside a regulated setting where personnel could observe how fog cooling of overhead gases prevented flashover. The program demanded significant physical and psychological commitment. Training compartments reached temperatures of 500 to 600 degrees Fahrenheit. Smoke reduced visibility to nothing. Trainees learned to rely on touch and instinct, to depend on their preparation, to maintain effectiveness when confronted with severe physical and mental stress. Many initially found it overwhelming, yet instructors guided them through fear toward mastery. The third day brought complex scenarios, handling a simulated hangar deck fire with aviation fuel burning, smoke obscuring the space, and pretend casualties requiring assistance. Sailors operated in organized teams, managing numerous hose lines, with some applying fog to cool environments while others drove forward with direct flame attack. They learned to maintain coordination in zero-light conditions, to help teammates to stay organized under near-combat pressure. The change was striking. Inexperienced sailors arrived hesitant or frightened. They graduated assured, having repeatedly put out severe fires with proven approaches. Afterward, many commented that genuine battle fires, though riskier from enemy actions and real injuries, proved less intimidating because comparable training conditions had prepared them mentally. Burke and Kildaff personally led 3 weeks of intensive instruction for the initial group of 260 instructors. These instructors would establish training programs at every major naval base throughout the continental United States. The standards for choosing instructors were rigorous. Candidates required firefighting expertise, instructional talents, technical proficiency, and commanding capability. Numerous originated from city fire services, reserve officers like Burke and Kildaff, who transported professional knowledge into military settings. The instructor preparation included firefighting procedures, instructional approaches, emergency practices, and apparatus servicing and learner assessment. Burke stressed that trainers must manage the equilibrium between authenticity and safety, push trainees sufficiently to establish genuine readiness without accepting unnecessary dangers. He communicated knowledge from his FDNY background regarding teaching firefighting, acquiring and reinforcing skills through practice, managing psychological responses to danger, and managing and overcoming apprehension. Following graduation, instructors distributed to various installations, expanding the program with consistent methodology. The firefighting program launched at San Diego Naval Base in August 1942, with Norfolk beginning in September. By December 1942, schools operated at Great Lakes, Charleston, Seattle, Pearl Harbor, plus numerous additional major installations. Every facility incorporated the same training constructions manufactured per Burke's blueprint, securing consistency across the whole fighting force. This consistency mattered tremendously. A sailor instructed at Boston applied the same procedures, hardware, and approach employed by a trainee at San Diego. When combined task forces operated as one, their damage management teams synchronized flawlessly. Command could count on every certified sailor utilizing the established methods, allowing reliable coordination and arrangement during engagement circumstances. Training expanded to encompass officers in dedicated programs covering firefighting methods, integrated damage management, and command decisions in burning situations. Burke demanded officers comprehend not merely what instructions to issue, but the underlying reasons, that they be prepared to examine firefighting performance and decide intelligently under challenging circumstances. Officer education comprised scenario simulations managing multiple concurrent fires, resource distribution, and priority decisions regarding which flames to extinguish initially. Through mid-1943, measurable improvements emerged. Tens of thousands of sailors completed training in fog technology. Fleet vessels sailing toward active theaters carried personnel assured of their capacity to combat fires skillfully. The transformation of attitude matched the development of technical abilities. Personnel stopped viewing fire as uncontrollable destruction, instead treating it as an opponent they possessed the capability to overcome. Yet instruction could not independently save vessels. The military required sufficient fog nozzles distributed throughout the complete fleet, and this production schedule needed aggressive acceleration despite wartime industrial restrictions. The Bureau of Ships pursued vigorous contracting for fog nozzle manufacturing, distributing production across multiple vendors to guarantee delivery velocity and supply chain resilience. Rockwood's Worcester-based sprinkler enterprise emerged as the lead manufacturer for the Rockwood Universal Fog Nozzle that Burke had championed. The firm's operation expanded for intensive manufacturing, introducing additional laborers and running continuous production runs to fulfill Navy specifications. By early 1943, Rockwood delivered many thousands monthly. The Bureau selected two primary configurations: nozzles compatible with 1.5-inch hose plus nozzles for 2.5-inch hose. This approach minimized supply complications and simplified preparation. Vessels would transport each measurement with smaller nozzles for routine application and bigger nozzles for serious fires. The adaptable design incorporated three settings: fog, solid stream, plus closed position, granting sailors numerous tactical selections. Extender attachments permitted operators to project fog into spaces unsuitable for direct entry, applying spray through doorways or air openings. Manufacturing fog nozzles demanded meticulous precision. The interior components generating the fog pattern required machining to exact specifications to maintain dependable performance at operating pressures and volume demands. Rigorous quality oversight was indispensable. A nozzle that failed when ships came under attack could mean lives lost. Rockwood knew this, which is why he put every single nozzle through rigorous testing. Pressure testing each one and visually inspecting the fog patterns before they shipped out. But getting these nozzles distributed across the Navy's sprawling fleet presented a whole different challenge that tested the supply system to its limits. New construction ships were the straightforward part. Fog nozzles went in as standard equipment in the damage control packages. The real headache came with ships already serving at sea. Those vessels needed retrofitting, which meant getting nozzles to forward bases scattered across where the fighting actually happened. The Navy created special supply channels just for damage control equipment, with fog nozzles marked as priority items that needed to move fast. Ships operating in the Pacific got their nozzles through the same logistics pipeline that delivered everything else: ammunition, replacement parts, you name it. Supply ships would carry fog nozzles out to forward anchorages, hitting places like Ulithi, Eniwetok, and Pearl Harbor. When ships pulled in for resupply and maintenance, those fog nozzles were waiting for them. Treated as essential cargo, by the end of 1943, most frontline combat vessels had at least some of these nozzles aboard. By the middle of 1944, nearly every ship that mattered had them. The shift away from solid streams wasn't complete, though. The old-style solid nozzles stayed aboard as backup gear and for specific jobs where they still had real advantages. Solid streams could reach farther. They were better for fighting fires from a distance. They cooled structures better from the outside. There were situations where you still wanted that concentrated force. Burke had never pushed to eliminate solid streams completely. His argument was simpler. Make sure fog nozzles were the main tool for the worst shipboard fires. Throughout ships, damage control stations got reorganized to keep fog nozzles front and center, stored with extension applicators, spare parts, and cleaning supplies right there. People developed maintenance procedures and taught them to crews. Fog nozzles needed regular cleaning to stop salt buildup from clogging those fine passages that made the fog work. Sailors learned to take them apart, clean them thoroughly, put them back together, test them regularly, spot worn parts and replace them. The money spent equipping the whole fleet was real, but it wasn't unreasonable. Fog nozzles were cheap compared to most naval equipment. Each nozzle ran about $75, which sounds like nothing next to millions spent on major weapons. A destroyer might carry 20 nozzles for $1,500 total equipment cost. A carrier might have 60 for $4,500. Across the entire fleet, you were talking hundreds of thousands of dollars, pocket change compared to what ships cost to build, and trivial against the worth of the ships and lives being saved. The real proof came when Burke's program got its first combat tests in scattered actions through 1943 and into 1944. Ships took hits, fires broke out, damage control teams trained on fog nozzle techniques saved vessels that probably would have gone down. Every success built confidence, reinforced that the training and equipment changes were worth it. In November of 1943, the light cruiser Birmingham caught a torpedo that tore open fuel tanks and started fires burning in 2 engine rooms. The damage control parties attacked with fog nozzles, using them indirectly through ventilation ducts to cool spaces too hot for anyone to get inside. 40 minutes later, the fires were under control and Birmingham kept operating after some temporary patching. Under the old way of thinking, they'd have flooded those compartments and probably lost the ship. Fog nozzles gave them another choice. Come January 1944, the destroyer Spence got bombed during the fighting in the Gilbert Islands. Those bombs punched through the main deck and exploded in the crew's sleeping areas, starting fires that tore through all that wooden furniture and bedding crammed into those spaces. Firefighting teams used fog patterns to cool the spaces next to the fire and keep it from jumping while they attacked the main fire head-on. That combination of quick knockdown and using just the right amount of water let Spence keep her balance and limp back to port under her own steam. But the destroyer LaFay gave maybe the most powerful early proof of how well fog nozzles worked. On April 16, 1945, off Okinawa, LaFay endured one of the worst kamikaze attacks of the entire war. In 80 minutes, that destroyer took 4 bomb hits and got crashed into by 6 kamikaze aircraft. Every single impact started fires. The crew fought those fires continuously, never stopping even as more kamikazes kept hitting the ship, using fog nozzles to push back the flames. These fires were fed by aviation gasoline from crashed planes, torn fuel lines, and burning wreckage everywhere. Solid streams would have scattered all that burning fuel, spreading the fire faster than anyone could have stopped it. Fog patterns put out the burning gasoline without spraying it around. They cooled spaces threatened by the fire spreading and used minimal water. They prevented the flooding that could have tipped over a destroyer that was already so badly damaged. LaFay made it through with 32 killed and 71 wounded. She stayed afloat, took heavy damage, but eventually got repaired. What she went through, fires everywhere at once during that intense attack, showed that if you trained damage control teams properly and gave them the right equipment, they could save ships even in conditions most people would call impossible. LaFay's story became famous throughout the fleet, proof that the training and those fog nozzles actually worked when things got worst. The battleship South Dakota proved it again in June of 1944. A bomb during operations near the Marianas went down and hit the ammunition handling room, where anti-aircraft gun rounds sat ready to fire. That explosion lit up the powder charges, and a fire started moving toward the main magazines below. If those magazines went up, South Dakota disappeared. Firefighting crews used fog nozzles with extension applicators, sending fog down through deck openings to reach the fire below. The fog cooled the space and made steam that took the oxygen out, suffocating the flames before they could reach the magazines. At the same time, other teams used fog to cool the magazines themselves. bringing the temperature down and stopping the ammo from detonating on its own. Within 35 minutes, the fire stopped and South Dakota stayed in action. The old methods might not have let people get close enough to stop the magazines from exploding. The carrier Hancock took a kamikaze hit on April 7, 1945, off Okinawa that went straight to the hangar deck and exploded around parked aircraft. That explosion touched off aviation gasoline and spread fire through the whole hangar. Damage control teams sent fog both directly at the flames and indirectly through ventilation systems, hitting the fire from every angle at once. The hangar's sprinkler system had been smashed by the explosion, so fog nozzles were the only real way to fight this fire. 70 minutes later, the fire was out. 62 men were dead and 71 hurt, but Hancock kept working and was launching strikes again within a few hours. These events, and many others like them, proved Burke had transformed how the Navy fought fires aboard ships. Ships that should have gone down were saved. Deaths that could have been in the hundreds became numbers that people could manage. The fleet kept fighting even under savage enemy attacks. Word spread through the Navy about how well these fog nozzles worked, building support and eagerness for what Burke had pushed so hard for. USS Franklin had already shown how valuable fog nozzles were before she almost got destroyed in March of 1945. Back on October 30, 1944, while operating near the Philippines during the Battle of Leyte Gulf, Franklin took a major hit. A Japanese kamikaze slipped through the fighter patrol and crashed down through the flight deck, hitting the hangar deck where 33 aircraft were getting ready for strikes. The explosion was massive. Gasoline from broken aircraft fuel tanks ignited right away, filling the hangar with flames. Bombs and rockets stored on those planes started cooking off, explosions on top of the fire. Ammunition for aircraft guns went off, sending shrapnel everywhere in that space. Within minutes, the whole hangar deck was burning. Franklin's damage control parties had been trained in Burke's methods. They moved fast with fog nozzles, setting up a coordinated assault from multiple directions. Teams positioned themselves at hangar access points and sent fog patterns into the space, cooling superheated gases and creating conditions where people could actually get inside. Other teams used extension applicators to reach areas burning so hot that direct approach was impossible, sending fog through ventilation openings and where the hangar had torn open. The fog patterns kept the fire from spreading to other sections while teams attacked the main body of flames. Multiple fog streams working together, making steam that pushed the oxygen out while cooling everything around them, proved incredibly effective against that inferno. The effort to save Franklin that October day went for 2.5 hours. The hangar temperature hit more than 2,000 degrees, hot enough to bend steel beams and melt aluminum. Solid streams would have done almost nothing at that temperature. The water would have flashed into steam before it ever reached the fire, barely cooling anything. Fog patterns, already designed to make steam, gave maximum cooling even at those extreme temperatures. The damage control teams worked in shifts, rotating people out when they'd had all the heat they could handle, bringing in fresh teams to keep the firefighting going. They advanced carefully, cooling things section by section, killing fires in areas they'd brought under control while making sure fire didn't start again. By 3 o'clock in the afternoon, the major fires were out. By 5 o'clock, the remaining hotspots were gone, and cooling had dropped the temperature enough for damage assessment teams to get into the hangar. 56 men died and 60 were wounded in that October attack, most when the explosion happened and right after. But Franklin survived and pulled out under her own power. Temporary fixes were done at Ulithi, and the carrier was back in action within 3 weeks. The official damage report said fog nozzle use and solid damage control training were what kept Franklin from being lost. That October experience taught Franklin's crew valuable lessons. They knew their training worked in real combat. They saw where they could do better with coordination and communication. They felt confident now that even massive fires could be controlled if you used the right techniques. That confidence mattered hugely 5 months later when Franklin faced damage that should have destroyed her. The real test of Burke's transformation happened on March 19, 1945, when USS Franklin suffered damage that should have sent her to the bottom. The carrier was 50 miles off the Japanese coast, part of Task Force 58, throwing strikes at airfields on Kyushu to support the Okinawa invasion. At 7 minutes past 7 in the morning, a single Japanese dive bomber came in low through heavy clouds, slipping past radar until it was too close for the anti-aircraft guns to hit properly. The pilot dropped 2 bombs that hit Franklin's flight deck and hangar deck in the absolute worst spots, at the absolute worst moment. 31 aircraft were sitting on that flight deck, completely fueled and armed with bombs and rockets, ready to launch for the morning's first strike. 22 more aircraft packed the hangar below, equally loaded and fueled. Those 53 aircraft carried more than 15,000 gallons of aviation gasoline. The ordnance included Tiny Tim rockets, 500-pound bombs, and ammunition by the thousands. The first bomb penetrated the flight deck near the center and blew apart on the hangar deck. That explosion ignited every plane in the hangar space instantly. Aviation gasoline sprayed from ruptured fuel tanks, creating a pool of fire spreading across the 400-foot hangar. The intense heat immediately started cooking off ammunition and ordnance on the burning aircraft. Near the number 3 elevator, the second bomb penetrated to the gallery deck, detonating in crew sleeping areas and killing dozens of men right away while starting fires on 3 different decks. Fuel lines burst, feeding more gasoline into the fires. The blast also damaged critical systems, fire mains, power distribution, communication systems. Within 2 minutes, a dozen Tiny Tim rockets tore loose from burning aircraft. These massive 11-foot rockets, each with a 138-pound warhead, became unguided missiles bouncing around the hangar. They smashed into walls, broke through into other spaces, and exploded when the warheads hit hard enough to detonate. Every explosion started new fires and sprayed shrapnel everywhere. Machine gun ammunition began cooking off by the hundreds of thousands of rounds. The constant rattle of bullets tore through thin walls, wounded or killed anyone nearby, and turned the hangar into a death zone. Larger ordnance started detonating as fires reached bombs and rockets on the planes. Each explosion sent shockwaves through Franklin, triggered more fires, and threw fireballs that spread flames to new areas. The death toll in those first 10 minutes was catastrophic. The initial explosions killed approximately 300 men instantly. Flight deck crews working on aircraft, hangar personnel getting planes ready, sailors sleeping in areas near where the second bomb hit. Hundreds more suffered wounds, many burned critically. Dozens got blown off the ship or jumped into the sea trying to escape. Franklin's medical areas filled up fast. When Franklin's engines lost power as smoke filled the engine rooms and crews had to evacuate, the ship went dead in the water, drifting 50 miles from Japan with fires raging across 4 decks. Radio systems were gone, so no one could call for help. Water from burst fire mains and firefighting efforts collected on the starboard side, tilting the ship 13 degrees and threatening to tilt more. In these desperate circumstances, Lieutenant Commander Joseph T. O'Callaghan, Franklin's Catholic chaplain, and Lieutenant Donald A. Gary, an engineering officer, organized the firefighting that would save the ship. O'Callaghan moved through Franklin, gathering anyone still able to fight. Cooks, office workers, storekeepers, anyone not already fighting fires or caring for wounded. Gary organized rescue teams to reach men trapped below by fire and smoke. They grabbed fog nozzles and moved into conditions that would have been impossible with traditional equipment. Many of Franklin's fire mains had burst, meaning water pressure dropped way below normal. With the electrical power gone, the pumps that usually kept pressure up weren't working. The hangar's sprinkler system was destroyed. Damage control teams had to work with whatever water pressure they could get, using portable pumps and bucket brigades in places where the mains had failed completely. In these rough conditions, fog nozzles showed exactly why they mattered. Solid nozzles needed significant water pressure to work right. At lower pressure, they would have been basically useless. Fog nozzles worked well even with reduced pressure, turning whatever water was available into fog patterns that cooled spaces and suffocated flames. The firefighting battle lasted 8 hours straight. Teams attacked fires methodically, deciding which fires to hit first, based on which ones threatened the most important spaces. The forward magazines got top priority. If they detonated, Franklin would vanish in an instant. Fog sent through ventilation ducts cooled these spaces enough to stop detonation, even as fires burned in compartments all around them. When the heat or continuing explosions made direct approach impossible, teams used extension applicators to send fog through doorways, ventilation openings, and where the hull had torn. The fog cooled things from a distance, gradually bringing temperatures down until people could get close. Teams worked in rotation, fighting until exhaustion, then stepping back while fresh teams took over. Gary led rescue teams into spaces where 300 men were trapped 3 decks down under the hangar. Getting there meant going through passageways where temperatures exceeded 500 degrees, with smoke so thick you couldn't see anything. Gary's teams moved forward using fog nozzles to create protective water curtains, the fog cooling the air enough to let them push through for brief moments in conditions that would normally kill you. They made 7 trips into that hell, each time bringing groups of trapped men back to where they could breathe. 252 men got out because of these rescue efforts. The light cruiser Santa Fe came alongside Franklin, a risky maneuver that put the 2 ships nearly hull to hull. Santa Fe's crew passed over extra fog nozzles, hoses, and portable pumps. Her pumps boosted Franklin's damaged systems, giving better water pressure for fighting fires. Santa Fe also took aboard 833 survivors, bringing wounded men aboard for medical care and moving non-essential people off Franklin to ease the pressure on her damage control teams. Throughout the day, the fire battle continued. Multiple times, it looked like Franklin would have to be abandoned. Fires kept threatening to reach the forward magazines, requiring immediate fog application to cool those spaces. The blasts continued to tear through the ship as ammunition exploded in rapid succession, each detonation claiming firefighters and igniting fresh blazes. The water flooding into the damaged compartments climbed steadily, reaching 17 degrees in temperature before countermeasures could finally stabilize the vessel. Yet slowly, almost imperceptibly, the situation began to shift in their favor. Through the afternoon hours, the major conflagrations came under control, though isolated pockets of flame continued their relentless burn. As evening approached, temperature readings throughout the ship showed a welcome decline. By the time night fell on March 19th, every major fire had been extinguished, though damage control crews would continue battling smaller flare-ups for days to come. The exact toll of lives lost and wounded became a point of historical contention. Samuel Eliot Morrison's official naval history documented 724 dead and 265 injured. Yet other sources, including reports from the Naval History and Heritage Command, recorded significantly higher numbers, 877 killed and 487 wounded. This disagreement arose from how casualties were categorized. Some accounting methods excluded air group personnel or Marines traveling aboard, while others counted everyone present. Some tallies included sailors who succumbed to their injuries weeks or months later, whereas others counted only those killed in the immediate aftermath. Either way, the numbers represented roughly 1/3 of Franklin's entire crew, dead or wounded. No other ship that survived the war suffered such devastating losses, and yet Franklin did survive against seemingly impossible odds. Despite destruction that appeared catastrophic enough to send her to the ocean floor, the carrier remained buoyant. Over subsequent days, improvised repairs gradually restored partial power to her engines. Franklin managed to travel 12,000 miles under her own propulsion, ultimately reaching New York on April 28, 1945. She arrived damaged almost beyond recognition. Her flight deck lay warped and charred black. The superstructure stood as a blackened skeleton. Her hull bore enormous scars from explosions rippling across her sides, but she floated, and her crew had brought her home. When the Bureau of Ships conducted its formal analysis of Franklin's survival, the conclusion proved absolute and unambiguous. The fog nozzles had been the decisive factor between total annihilation and survival. Without them, officials concluded, the ship would have been abandoned and deliberately sunk within hours of that morning's attack. The fog nozzles accomplished precisely what Buck had envisioned. They functioned reliably, even at reduced water pressure. They cooled compartments efficiently using minimal water. They suppressed burning aviation fuel without dispersing it into fresh flames, and they created steam that suffocated spreading fires. These exact capabilities that Buck had fought so fiercely to implement had proven absolutely essential. Both O'Callaghan and Gary earned the Medal of Honor for their extraordinary heroism in saving Franklin. The White House ceremony took place on January 23, 1946, with the medals officially presented. Their citations highlighted their skillful deployment of damage control systems, though fog nozzles weren't mentioned explicitly by name. Navy training programs subsequently made Franklin's survival their textbook example of damage control excellence under extreme duress. Buck's innovations reached far beyond a single ship's fate. The broader impact of enhanced damage control systems transformed strategic thinking throughout the Pacific theaters. Carriers could now operate within striking distance of enemy bases, accepting the risk that kamikaze damage might be survivable instead of automatically fatal. Amphibious assault forces could undertake more aggressive shore bombardments, trusting that ships struck by coastal guns could potentially be rescued rather than lost. The fleet sustained higher operational intensity because damaged vessels returned to combat faster. After the war, Admiral Chester Nimitz, commanding all Pacific Fleet operations, analyzed which factors had proven critical to victory. He specifically identified improved firefighting capacity, particularly the widespread adoption of fog nozzles and corresponding training protocols, as having been essential for maintaining operational strength during the war's final months when kamikaze assaults created relentless demands on damage control systems. Buck's program, measured in cumulative lives spared, numbered in the thousands. Each preserved vessel meant hundreds of additional sailors going home rather than perishing in flames or sinking seas. Franklin herself sheltered approximately 2,000 men still aboard when her fires were finally conquered. Had she gone down, nearly all would have died. The many other ships saved through proper fog nozzle application each contributed additional survivors. The financial consequences were equally staggering. Every major warship saved represented millions avoided in construction expenditures. A single fleet carrier required approximately $70 million to construct and 2 years to complete from keel laying to commissioning. Franklin's salvation alone justified the entire expense of Buck's training initiative many times over. The combined savings from numerous surviving vessels reached hundreds of millions. Yet perhaps most significantly, Buck's achievement demonstrated that even tradition-bound military cultures could embrace genuine innovation when proper advocacy occurred. He had confronted centuries-old naval practices head-on, withstood institutional opposition at every stage, and ultimately achieved comprehensive change in both equipment and methods. His success proved a vital principle. Sometimes the most transformative military developments come from outside military structures, from civilian specialists bringing entirely different knowledge and approaches. Beyond the hardware and instructional methods, Buck fundamentally reshaped naval thinking about damage control itself. In 1941, firefighting occupied a secondary role, something attempted only after primary systems failed. By 1945, damage control had risen to primary status, recognized as fundamental to combat effectiveness. Damage control teams joined the ranks of elite units, receiving training standards equivalent to gun crews and undergoing equally rigorous evaluation. The psychological transformation ran equally deep. Sailors in 1941 saw fire as an unstoppable force and damage control as a desperate gamble unlikely to succeed. By 1945, they confronted fires aggressively, grounded in confidence in their preparation and capabilities, viewing blazes as tactical challenges rather than doom. This mental shift from resigned fatalism to determined confidence marked a profound cultural change. Officers came to understand that damage control demanded the identical careful planning and investment of resources that offensive operations required. Pre-war battle planning now included strategically positioning damage control squads and verifying that equipment remained ready and accessible. Officers studied probable damage scenarios in advance. During actual combat, commanders monitored damage control efforts with identical intensity as tactical situations, making critical allocation decisions that could determine whether vessels survived. The standardized training produced a unified culture across the entire fleet. Sailors trained at separate bases absorbed identical procedures and techniques, using consistent terminology across damage control operations. Officers could depend on standardized capabilities and coordinate seamlessly across different squadrons. This consistency extended throughout equipment maintenance, tactical procedures, and the very language used to describe firefighting approaches. Burke's revolution in naval firefighting proceeded simultaneously with parallel advances in Coast Guard methods. Lloyd Laman, who had created indirect fog application systems as a civilian fire chief before enlisting, received a commission as a commander in the Coast Guard and assumed command of the Firefighting Training Center at Fort McHenry in Baltimore. Laman undertook rigorous scientific research into fog nozzle applications, utilizing the Liberty ship Gaspar de Portula as his testing ground. His investigations determined ideal droplet dimensions, fog configurations, and application procedures suited to different fire scenarios. His research appeared in Fire Engineering magazine in February 1945, offering scientific backing for methods Burke had championed based on operational results. Following the war, Laman rejoined civilian fire service as chief of the Parkersburg, West Virginia Fire Department. He transported the naval fog techniques he had refined during combat years into structural firefighting, fundamentally transforming how city fire departments battled building blazes. His 1950 presentation to fire department instructors demonstrated how indirect fog application extinguished structural fires far more efficiently than traditional solid stream methods. Laman's contributions ensured that naval combat lessons transformed firefighting globally. The techniques Burke had championed for preserving ships revolutionized the protection of buildings. Fog nozzles became standard issue across fire departments worldwide, prized for their flexibility and performance against numerous fire varieties. Burke continued his service through war's conclusion and into the post-war years, refining fog nozzle methods and training fresh instructors. In July 1947, he received appointment as chief of the New York City Fire Department, the highest position in municipal firefighting leadership. He assumed office on August 1, 1947, but surprisingly retired immediately upon his appointment. The exact circumstances surrounding Burke's brief tenure remain somewhat mysterious within historical documentation. Fire Engineering magazine reported on August 1, 1947, that Chief Harold Burke stepped down immediately after taking the position. The role remained unfilled until Peter J. Loftus accepted appointment on August 1, 1948. During his limited time in the position, Burke pushed the FDNY to implement Navy-developed training approaches, including realistic fire simulators and coordinated tactical responses. Burke's later years remain largely absent from historical records. No date of death appears in accessible documentation, and his final decades remain enigmatic. He faded from public prominence after retiring, leaving behind a heritage measured through rescued vessels and preserved lives instead of formal recognition or awards. Fog nozzles stayed standard equipment throughout the United States Navy for decades following widespread adoption. Although specific technologies advanced and modern innovations emerged, the fundamental concepts Burke promoted, that fine water droplets deliver superior cooling and steam production compared to heavy streams, remained central to naval firefighting throughout subsequent decades. The subsequent major transformation in naval firefighting emerged following the catastrophic USS Forstall fire on July 29, 1967, in the Gulf of Tonkin. An accidental Zuni rocket discharge crossed the flight deck, striking a loaded aircraft and rupturing fuel containers. The resulting inferno and detonations killed 134 personnel and injured 161 more. The catastrophe exposed ongoing deficiencies in damage control systems, particularly concerning foam-based suppression for aviation fuel. AFFF, aqueous film-forming foam, had received Navy patent protection in 1966, though wasn't yet deployed throughout the fleet. The Forstall disaster necessitated mandatory adoption of AFFF systems fleet-wide and a thorough restructuring of aviation firefighting approaches. Fog nozzles, however, remained essential damage control tools, valued for versatility and effectiveness against various fire categories. AFFF represented supplementation to fog nozzle methods, not replacement. Into the 70s and 80s, fog nozzles continued as standard damage control hardware aboard all Navy vessels. Subsequent sailor generations studied identical fundamental techniques Burke had pioneered, tailored to modern ship construction and developing fire threats, yet unchanged in their essential nature. Fog nozzles persisted because they functioned effectively, because they tackled multiple problems efficiently, and because the thermodynamic principles of heat dissipation through water surface remained invariant regardless of innovation elsewhere. Burke's contributions transcended naval boundaries. Fire departments globally integrated fog nozzles in the post-war period, encouraged by Navy combat demonstrations and by military veterans bringing naval firefighting methods into civilian services. Adoption proceeded gradually but steadily. Fire departments that had rejected fog nozzles previously found compelling evidence in naval combat applications. Petrochemical facilities and refineries embraced fog nozzle technology for superior performance controlling flammable liquid blazes. Industrial fire brigades employed equipment and procedures created by Burke and Leman, seeing that petroleum fires in industrial contexts posed difficulties comparable to shipboard conflagrations. Fire service training integrated lessons from naval combat. Academies constructed training structures mirroring naval designs, producing realistic fire conditions where students encountered genuine heat and smoke approximating actual incidents. Instruction moved from theoretical classroom discussion to hands-on experience, from academic descriptions of firefighting to actually suppressing fires in controlled settings. Burke's foundational concepts became globally standard within fire science instruction. Fire engineering programs covered the thermodynamics of cooling and steam generation. They analyzed maximizing water surface exposure, the operational applications of fog patterns versus heavy streams. What had been dismissed as revolutionary thinking in 1941 had transformed into established knowledge by 1950. It appeared in fire academy curricula worldwide as accepted practice. The account of Lieutenant Harold J. Burke and the fog nozzle reveals crucial insights regarding military innovation and institutional transformation. Recognizable patterns emerged that remain applicable for contemporary military organizations, navigating technological and doctrinal evolution. Fundamentally, revolutionary change regularly emerges beyond military borders, from civilian experts offering fresh viewpoints and specialized knowledge. Burke achieved success not through inventing fog nozzles, they pre-existed his crusade, but through importing municipal firefighting knowledge into military contexts and maintaining resolve despite organizational hostility. His civilian perspective generated insights internal military development probably never would have reached. Additionally, conquering bureaucratic opposition requires demonstrating observable superiority under authentic scenarios. Burke's arguments and theoretical presentations persuaded no one. His methodical demonstration presenting measurable fog nozzle results versus traditional approaches delivered evidence no one could dispute. The demonstration format, authentic fires, consistent conditions, and numerical verification proved essential to establishing credibility. Furthermore, transformation demands institutional advocates possessing adequate authority for enforcing change. While Burke's abilities and demonstrations mattered greatly, Admiral Cochrane's backing proved indispensable for surmounting institutional resistance and implementing fleet-wide adoption. The fusion of external specialized knowledge and institutional authority proved transformative. Sixth, scaling innovation requires consistent instruction. Confirming techniques transmit systematically. Burke didn't restrict training to select units, but designed expandable programs producing hundreds of instructors who prepared thousands of personnel to matching standards. This regularity guaranteed fog nozzle adoption, produced genuine capability, not simply distributed tools. Seventh, institutional opposition to change originates from various sources requiring distinct solutions. Burke faced technical doubt concerning fog nozzle functioning, which demonstrations addressed. He encountered psychological skepticism about apparently insufficient apparatus, which he resolved by displaying tangible outcomes rather than specifications. Bureaucratic resistance to acknowledging flawed prior approaches yielded when he framed change as advancement rather than correction. Financial hesitation faded when he proved equipment expenses seemed negligible against ship preservation. Burke's achievements contain lessons valuable for modern military organizations. Technology constantly advances beyond doctrine, producing persistent disconnects between possibilities and implementation. Civilian professionals in specific domains frequently possess capabilities military institutions don't. Yet military tradition occasionally rejects outside contributions. Transformation demands surmounting identical opposition forms that challenged Burke. Skepticism regarding technical function, discomfort regarding unconventional methods, administrative gridlock, budget constraints. Contemporary military organizations would gain from structured systems, identifying, examining, and adopting civilian innovations. Burke's fog nozzle innovation shouldn't have awaited Pearl Harbor's devastation for attention. Preliminary mechanisms evaluating municipal firefighting developments could have eliminated casualties that precipitated transformation. Collaboration across military and non-military sectors accelerates development in both contexts. Burke transported civilian knowledge into military settings, expanding naval superiority. Lamon transported military experience into civilian firefighting, revolutionizing municipal services. The contemporary military should deliberately facilitate comparable exchanges, recognize civilian sectors possessing applicable expertise, create channels enabling information circulation. Harold J. Burke's narrative illustrates history's frequent neglect of its greatest contributors. Burke never commanded fleet operations or achieved famous battlefield triumphs. His contribution proved quieter, though equally impactful. He equipped the United States Navy with capabilities and instruction, preserving thousands of sailors and numerous ships. He revolutionized Navy perspectives regarding fire and damage control, developing aggressive, trained firefighting approaches persisting presently. He demonstrated that occasionally history's finest discoveries come from unexpected quarters. From someone, a New York City firefighter, who recognized that distributed water performed better than torrential discharge, that preparation surpassed custom, and that preserving lives superseded protecting reputations. When USS Franklin traveled beneath the Statue of Liberty on April 28, 1945, she presented concrete evidence of Burke's accomplishment. She bore visible damage and scars, yet remained afloat, carrying hundreds of personnel still alive who otherwise wouldn't have survived. Burke wasn't present at her arrival. He stayed teaching the subsequent generation of damage control instructors. Yet his contributions sailed past that statue in the form of a destroyed vessel that endured rather than sank. That represented sufficient memorial for someone desiring nothing beyond the awareness that his efforts created genuine difference. The vessels he rescued, the individuals he preserved, the firefighting methods he reshaped, these quantify Lieutenant Harold J. Burke's genuine significance toward success. His account merits prominence alongside more celebrated innovations, not from his desire for recognition, but because comprehending how fog nozzles came to rescue numerous vessels illustrates how committed persons modify institutional behavior, how outside knowledge improves military effectiveness, and how occasionally modest technical modifications generate extraordinary strategic ramifications. The fog nozzle innovation Burke championed demonstrated that transformation prospers not exclusively through hierarchy, but via determination, proof, and bravery to question assumptions in cultures most resistant to innovation. His influence lives in every ship preserved by proper damage control, in every firefighter instructed to encounter flames with assurance instead of terror, and in the principle that danger resembles opposition and yields when personnel possess appropriate equipment, thorough training, and conviction that preparation ensures triumph.